Welcome to the course Stream Processing in Apache Flink for Ambient Assistant Living. In this first video, we are going to give a short introduction into, first of all, we are going to see what is actually big data and why it's an important segment of our lives nowadays. Then we will see some of the most famous frameworks for processing of big data, both in stream and in batch fashion. And afterwards, we're going to get familiar with Apache Flink, which is the framework of choice for this course for stream processing, concretely for big data or data related to ambient assisted living. Um, for this framework in this video, we are going to get familiar with some of the most important aspects of its infrastructure and architecture, and we are going to get familiar with the architecture itself. In the next videos of this course, we are going to see how can we create our own short application in Apache Flink using the Java programming language, using integrated development environment for Java. In our choice, it will be IntelliJ. How to connect all of that with build automation tool Maven in order to include all of the necessary dependencies for application of this type, and we will get familiar with all of the operators for stream processing that Apache Flink is allowing us to use in its applications, how to use them, how to declare them, and all of that will be shown with solving concrete tasks in the field of ambient assisted living. So we will see some log data from sensors, and we will process those simulated log data from sensors. We'll try to process it in real time, which is the goal of this course. So first, let's get started with introduction to big data. Big data is a really famous buzzword that we hear it all the time. So let's get familiar with the six V's of the big data. So when big data as a term was coined first, it contained only three V's: the volume, the variety, and the velocity. But over time, also other V's were added to the description of big data. So first we have the volume. So the volume represents the amount of data from myriad sources. So big data is actually enormous, while traditional data is measured in familiar sizes like megabytes, gigabytes, and terabytes. Big data can be stored up to petabytes and zettabytes. Yeah, just to grasp the enormity of the difference in scale, consider this comparison from the Berkeley School of Informatics. Information: 1 gigabyte is the equivalent of a 7-minute video in HD, while a single zettabyte is equal to 250 billion of DVDs. This is just the tip of the iceberg, according to one report. The digital universe is doubling in size every 2 years, and by 2020 is expected to reach 44 trillion zettabytes, uh, which is even now increased as we are in 2022. Big data provides the architectural handling of this kind of data. Without the appropriate solutions for storing, processing, it would be impossible to mine the data for some insight. Then we have the second V, of the traditional three V's. That's the variety. So the we have different types of data that can be considered as big data. First, we have some structured data. Then we have semi-structured and unstructured data, and so actually roughly 95% of all data is actually unstructured, which means it doesn't not fit easily into a straightforward traditional model for big data mining. What do we mean by unstructured data? That's everything from emails and videos to scientific and meteorological data, sensor data, etc., etc. All of these can constitute a big data stream, each of those with their own unique attributes. So we must investigate into how to handle those kind of unstructured data. The third of the traditional V's is the velocity of the data, and that means that is actually the speed at which big data is being generated. So it depends on the source of the big data. For example, if we consider as a source of the big data, for example, Facebook, which is a tool used by billions of people nowadays, we can see that the velocity of the data over there, for example, is huge. So by velocity, we mean we take it from the speed at which the data is created to the amount of the time that we need to analyze that data. So everything about that is actually fast. Um, Companies and organizations nowadays must have the capabilities to harness this data and generate insights from it in real time, which is actually one of the most important segments of this course: how to handle this kind of data real time. If we don't handle this data in real time, it is not actually very useful. Real time processing allows decision makers in companies or other stakeholders to act quickly, giving them a leg up on the competition of their companies. While some forms of data can be batch processed and remains relevant over time, much of the big data is streaming into organizations at a clip and requires immediate action from the best outcomes. Sensor data, for example, from health devices or other devices, is really a great example of this. So, the ability to instantly process health data can provide both the patients and the physicians with the potentially life-saving information at given times. Now we will come to the other three V's, which were added afterwards. The definition of the big data term. So um, the next one is the veracity, which represents the degree to which big data can be trusted. So veracity refers to the degree of accuracy in datasets and how trustworthy they are. Raw data collected from various sources can cause data quality issues that may be difficult to pinpoint. If they aren't fixed through data cleansing processes, bad data leads to analysis error, outliers, anomalies, etc., and those can undermine the value of business analytics initiatives. Data management and analytics teams also need to ensure that they have enough accurate data available to produce the wanted valid results. Um, some data scientists, data engineers, and consultants also add value to the list of big data's characteristic. So the value means the business value of the data that's collected. Not all of the data that's being collected through some sources has real business value or benefit. Some of them should be ignored. Uh, as a result, organizations needs to confirm that data relates to relevant business issues before it's used in big data analytics projects. This can also help saving some costs during the processing of the big data, which can be tremendous depending on the platforms, on the computational resources that are being used. The sixth V that we're going to consider in this presentation is the variability. That means the ways in which the big data can be used and formatted. So the variability also often applies to sets of big data, which may have multiple meanings or be formatted differently in separate data sources, or those are factors that further complicate big data management and analytics. So that's actually all of these six V's that define the concept of big data. Now we are going to see how we can, which frameworks, which data engineering frameworks we can use to process big data. We are going to consider four of them just for the sake of this introduction to big data, and then of course we will focus to the most important one for our course, that is the Apache Flink framework. So first, we are going to start with Hadoop. What's actually Hadoop? Hadoop is a software tool for security, for secure, scalable, and distributed processing of data in a cluster of computers and computer systems with the help of simple programmatic models. Hadoop can be used to also to store files uh, with to to store files that have the same intention of processing. Hadoop can store and process up to petabytes of data. And Hadoop as a solution is composed of three main components. First, we have the HDFS, Hadoop, that's acronym for Hadoop Data File System, directory file system actually. So that's a directory file system which is in charge to store data in a cluster of Hadoop. Then we have the MapReduce system, which is a system that is intended to process huge amounts of data in the Hadoop cluster. And then we have Yarn, which is actually the core that handles all of the resources. So all of these HDFS, MapReduce, the clusters itself, they are complicated resources that need to be managed by someone. And in this case of Hadoop, that is the Yarn, the core Yarn. Then we have MapReduce. MapReduce is a software tool to where you can easily write application to parallelly, concurrently process huge amounts of data, like several terabytes datasets. On huge clusters, those clusters can have up to 1,000 cores, and the processing of this data with MapReduce can be secure and fault tolerant. Uh, the system processes the data as records, and it processes those records in three phases. The first phase is the map phase. So the map phase is actually a previous processing and filtering of the necessary data. Then we have the second phase, which is the shuffle phase, or the workers in the process are sorting the data according to a given defined key. The key is defined by the previous phase. So in the shuffle phase, all of the data that is in the same key goes to one, let's say, partition. And lastly, but not least, is the reduce phase. The reduce phase is actually a user-defined function to reduce the data that is being sent to a given partition based on the previous two phases, the map and the shuffle phase. And this reduce is actually a aggregation function that will calculate on all of the data collected on a given partition. Then, as a third framework in here, we have Apache Spark. Apache Spark is a software framework with open source code, uh, which is uh, which is created as a more advanced solution in comparison with Apache Hadoop. The starter framework is built to work with big data, and the main difference between Hadoop and the Apache Spark is the model on how to find data. So Hadoop is storing all of the data on a hard disk together with each step of the MapReduce algorithm, while Spark does all of these operations using random access memory, the RAM memory. Because of this, Spark shows definitely better performances, and it allows processing of massive data streams. The functional and main characteristics of Sparks are better performance and fault tolerance. So Spark has four components: the core, Spark core, and four libraries that can optimize the interaction with the big data. One of them is Spark SQL, which is one of the four framework libraries that are used for structural processing of data. Spark also has on its disposal the streaming tool to process data in real time. But according to the results of different testings and benchmarks, this tool actually seems more like a processor for data which are represented in micro batches rather than processor of real time of data streams. So here we have the picture on which we can see the difference. On the x-axis on this picture we can see the throughput rate of the data. from left to right, it gets increased in how many events per second we are using for generation and consumption of the events. And on the y-axis, we can see the 99th percentile of the latency in microseconds. So here, this line over here represents the latency in the Spark framework, and we can see that the latency over here increases in almost a linear fashion as the throughput rate of the events per second increases. While in other frameworks like Flink, that we are going to focus in this course on, and Storm, are way much better, and they provide actually low latency processing of the data, which causes to process the data in real time or near real time. Um, so Therefore, we are going to get familiar with the fourth framework, and the one that we are going to focus most. That's Apache Flink. Apache Flink is a robust framework for processing of big data. So we can use Apache Flink both for stream processing, which is the focus on this course, and we can use it both to process batch data, the same, actually pretty much the same thing that Apache Spark is doing. Firstly, Apache Flink was defined as part of a scientific experiment somewhere around 2008, and then it became open source software around 2014. After that, it gets huge popularity as a framework. Flink has some interesting characteristics that we're going to see in the next slides. Also uses new impressive technologies. Flink uses stateful computations in order to process the data streams. It's in that is actually similar to Apache Samza, but also Flink can be used in some ETL processes for batch processing of the data with decent efficiency. Flink is a great choice for simpling the architecture where you need to have both stream and batch processing. Flink is uh, Flink is able to extract timestamps from the data in a way that you will define for Flink how to do it. From also Flink, Flink from the stream data can create a more precise time estimation and better analysis of the data. Flink also provides the possibility to implement some of algorithms for machine learning. Also allows us to use model serving of already created machine learning models. Flink is also part of the ecosystem Hadoop, so therefore it can be integrated with existing architecture without any issues. Flink can interact with both MapReduce and Storm in order to execute the already existing applications, and Flink has a good adjustability to big data. Uh, Flink is really good adjusted to design and implement applications that are driven by events or event-driven applications. Usually, it's using it's using checkpoints in order to save the current status of the processing in order of to to have a better way to retrieve the state of the system in case of fault of failure of the system. Flink also has the possibility to connect with the famous application for visualization of data, Apache Zeppelin. Flink was bought by Alibaba. Alibaba used Apache Flink to observe the customer behavior and to rank the search on the on some holidays when Alibaba has a lot of interactions on its website. As a result of that, the sale in Alibaba got increased for 30%. The finance giant ING used Flink to construct application to detect frauds and notify customers about that. And besides that, as we already mentioned, Apache Flink has algorithms for can use algorithms for machine learning. Uh, Other frameworks besides these four that we have mentioned so far are Apache Samza, Apache Storm, Apache Heron, Apache Kudu, Apache Hive, etc., etc. So there are a lot of frameworks, And it's really most important to emphasize this, that when you're choosing a framework to process big data, you always must to be driven by your use case scenario. So if you go by the popularity of the frameworks, Apache Spark would always be the first choice everywhere, and this can be a mistake. Apache Spark is not the best framework of choice for any kind of scenarios, as we already discussed about that. If you want to process uh, streaming data in real time, then Apache Spark will provide huge latency, and it won't be even near real time. So therefore, in this course, because we want to process streaming data for the purposes of ambient assistant living, we are going to use Apache Flink as a framework, and we are going to see why it's the most decent tool to process streaming data. So now that we have decided and explained why we need to use Apache Flink in this course, we will get familiar with some of the important aspects of Apache Flink framework. So as we said previously, Apache Flink can process both in batch fashion and in stream fashion. So what also another thing is that Apache Flink can process unbounded and bounded data. So what does that mean for what is actually bounded data? A bounded stream of data, is actually a stream that has both start and end. Okay, so for example, this is a stream of data, and these two actually represents bounded streams over here, because they both have starting timestamp and ending timestamp. We know when the stream will end. Completely opposite of that, we have the unbounded data streams. So they just have a start of the stream, for example, here or here, and we don't have an end of those. So actually, the end is infinity. It's not defined. It can be defined as the moment when the application will fail in a given moment. But if we provide fault tolerant application, then that can be forever until the application is running on a given cluster. That's the first really important aspect of why we can use and we should use Apache Flink. The second one is that an Apache Flink application is deployable anywhere, everywhere, wherever you need it. Um, so you can deploy the application. You can deploy the application on a Yarn cluster, on a Mesos cluster, on a Marathon cluster. You can use Docker to import it. You can use whatever possible tool for deployment that you want to use. Um, Nextly, in this part of the presentation, uh, we have that Apache Flink applications are really scalable. Apache Flink applications can be used to process 10,000 records per second, but they can also be scaled to process up to billion records in a second if it's necessary. You just have to define the architecture, the hardware behind the clusters where the application is running in the best possible way, and you can run the application at any scale. And the fourth, and this is quite one of the most important segments over here, is that Apache Flink can leverage in-memory performance. So what does that mean? For example, we have some tasks over here, for example, 3 of them. Um, what does that mean? For example, if we have some aggregation of the data that comes as an input, and we want to, let's say calculate the average of some numeric value of the data in a given time period. So in order to calculate the average, we are going to we will have to keep at least two numeric variables in a state at a given moment. That would be the sum of the data and the count of the data. and then we can divide that sum with the count of the data. But in order to do that, we need to store that sum and that count of the data records somewhere that would be really really fast to access that those two numeric variables. Why? Because, as we said, we want to have this to be in real time or near real time. Therefore, Apache Flink allows us to store those kind of information in a state, and that state can be actually a local state, in-memory state, on-disk state. And also, as we previously discussed, we can save this state periodically uh, with the concept of checkpoints and snapshots. We can save that state in some kind of durable storage. That durable storage can be a S3 bucket, can be a rock database, etc., etc. So this is actually what makes Apache Flink's one of the fastest library to process streaming data. Over here, we are going to now get familiar with the details of the Apache Flink architecture. So, what is actually Apache Flink as a processing engine doing? Apache Flink can be used to write event-driven applications, can be used to write streaming pipelines, what we are going to actually use, and also stream and batch analytics. We are also going to use that. So Apache Flink can read data from two kind of sources. We are going to see more detailed sources later, but initially it can read data from real-time events, and those real-time events can be transactions, logs, log data for Internet of Things, clicks on a given website, etc., etc. So all of those can be streamed in real time with with some stream processor or streams storage like Apache Kafka or some message brokers like RabbitMQ, and they can be ingested in real time in the pipeline in the framework. But also they can be that's how you read streaming data, but also they can be read in batch fashion from databases, from file systems, from key value stores, etc., etc. As we already said, Apache Flink is deployable everywhere, so you can deploy it on Kubernetes, on Yarn, on Mesos. Regarding for the storage of the local state, if we want to enable checkpointing, the storage can be done in a Hadoop distributed file system, in S3 buckets, in NFS, etc., etc. Um, the result of the results of this part of the application of the processing application can be sent to a different application, for example application for visualization, and it will provide the analytics on some beautiful dashboards. It can be sent as event logs to some place, and then they can be used for some other processing. And also at the end it can save the results in a given database or a file system or a key value store. And finally, we are going to really go deep into the Apache Flink architecture over here. So, how does Apache Flink work? First step in Apache Flink is the programmer or us. We have to define a program code. The program code for Apache Flink can be defined in mainly three languages: Java, Python, and Scala. We are going to see how to do that with Java over here and using Maven as a build automation tool. Then this program code, whenever we want, it's going to get sent to the optimizer or the graph builder. So the graph builder we will compose a graph data flow graph of several operators, all of the operators that we are going to define. All of those operators can be executed in tasks, in one or more tasks. If we want it to be in one task, that means that it's not using a parallel processing of the data. But if we want to enable parallel processing of the data, distributed processing of the data, then a given operator can run on several tasks. Uh, then the client, in this case, actually the client is the person who is running the application, can submit the job. Well, what do we mean by job? By job, for example, if we use a Java or a Scala code, the job is actually a jar file that is being created from the application. That jar file is being submitted together with the data flow that's created on a job manager. The job manager serves as a application master in this case. So the job manager is the one who receives the job, is the one who has scheduler on where to run the job, one who is a checkpoint coordinator, or it coordinates when the application will save its current state into some durable storage. And also, the job manager is the one that works with the concrete workers. So he is the master, and also we can have several workers. We need at least one worker, at least one task manager. But also, if we want to have the application to be more distributed, we can create more nodes. Each of those workers actually can help us to run the application in a distributed fashion way. For example, in this situation, in this visualization, we only have two workers, so that means that we can make the applications to run on two parallel nodes. But besides running on two parallel nodes, the multi threading, the we can have processing on several instances. Also, that depends on the task slots that the task manager has, so we can run the operators concurrently, and that depends on the number of nodes and how many task slots that task manager has. So in this situation, both of our task managers have three task slots. That means that we can run a given operator in six concurrent slots. That's how we can do it. Each of the task managers, as said, has task slots where a given task can be assigned to work. The assignment of those tasks is done by the job manager as well. Each of the task managers has is memory and input output manager, and this is needed in order for the local state to work. It also has a network manager, and this is how the network manager is actually how the data streams are being shared between the task managers when it's needed, when we want to provide distributed processing of the streaming data. And all of them have an actor system, just like the client, just like the job manager, which actually provides the communication between the job manager and the task manager, between the client and the job manager. Why is this actually as actor system needed? So the actor system can order the task manager to be deployed, to be stopped, or to cancel any of the tasks, to assign the tasks a given job. It can trigger checkpointing the job manager because he's the scheduler. Also, the actor is used in order to send task status, heartbeat, statistics of the jobs from the task manager to the job manager. And then this one aggregates those statistics, and it is sending those statistics and status updates to the client who is actually running a given Flink job. Uh, so that is pretty much how this architecture works. All of these, the workers, the job manager, they represent an Apache Flink cluster. This is something that we are going to get familiar with during this course. So an Apache Flink cluster is where the job can run. And as we said previously, we must have one job manager and at least one task manager in order to start an application of the Apache Flink framework. In the next videos, we are going to start with practical exams.